We're going to start our discussion of linear algebra by studying systems of linear equations. And here is an example of a system of linear equations. So we call them equations because, well, they are equations. Linear because if you look at one of these equations, at this stage in the course, I'll just say, notice that all the terms are linear. There's nothing quadratic, there's nothing cubed, there's no exponentials. Right? So linear seems like a natural terminology. Now there is a more sophisticated point of view on why we call these linear equations that we'll talk about later in the course. For the moment, I think the intuition is reasonable. And it's a system because, well, we're not just considering one equation at a time. Right? I'm not looking for a solution to this equation, comma, a solution to this equation, comma, etc. I'm looking for a solution, namely x1, x2, x3, etc. through xn, which satisfy all of these equations all at once. The same intuple, x1, x2, x3, etc. has to satisfy all of the equations. So this is not just in separate equations. This is a system of several equations. Okay, so we're going to ask some natural questions in advance. How do we know if there's a solution to the system? Could there be more than one solution? Perhaps. Maybe. Right? There's no particular reason to just rule out the possibility of multiple solutions. And if there are multiple solutions, how many? So these are reasonable things to wonder about. Now, I think most students have seen these kinds of questions at some point in the past, perhaps in Algebra 1 or Algebra 2 class. I saw them when I was in such courses described as simultaneous equations. And I was shown what I'm going to call a bad method for how to solve simultaneous equations. It was appropriate to the context, I suppose, but it had problems. So here was the method. Being asked to solve this system, the idea was that you take two of the equations and you combine them in some way or another to get a new equation. Now you'll notice what I've done here is I've added those two green circled equations. And that gives me this now fourth equation. Okay. Now the thing is, we started off with three equations. Now we have four equations. And then you can repeat. Take another two of the equations and combine in some way or another. And eventually, if you like, you can take equations that you have created by this method and combine them in some way or another to get other equations. So manipulating and combining equations like this until hopefully eventually you get an answer. Now, of course, there are strategies for how to use this this tool effectively, and I was advised to try to get rid of all of these variable and strategies of things to hope for. But what remained is that there were looming questions. It was never addressed how I would know that this would necessarily ever end this process. Right? How would I know? How do I know? It's not immediately clear whether it would or would not ever end. If it does end and you get a solution, how do you know that's the only solution? Well, that was never addressed either. And here's an even worse, nasty little issue. How do I know that the seeming solution that I found, how do I know that that actually is a solution? And I'm not talking about the possibility that I might have made an arithmetic error. There is a nastier issue in play, and let me show you an example of what I'm talking about. Let's consider this equation. And, of course, we all, at a glance, can tell that this equation has no solutions. Of course, right? There is no number that is equal to itself plus 1. And yet, watch me solve this equation. So I square both sides of the equation to get this. All right, and then we cancel x squared from both sides. And take the 2x, move it to the other side, divide by the coefficient of -2, and bam, we get what would appear to be a solution to this equation. I mean, correct me if I'm wrong, but we took an equation, we did perfectly legal algebra, and we got an answer. Now, obviously it's not a solution, and it's easy to take this and plug it back into there and confirm that that equation simply does not work. But how is it that we got a seeming, an alleged solution when clearly no solution exists, and furthermore, very clearly this itself is not a solution? Well, this is an interpretation problem. These steps here are legal. The problem is in how I interpret my result. What I have shown here is that if there were a solution to that equation, then the solution to that equation would also have to be a solution to this equation. That is a true statement. And if there were a solution to this, it would have to satisfy that equation as well. But that's not the interpretation I took. Right? The interpretation I took, and that students, I believe, are accustomed to taking, is that when you take an equation, you do legal algebra, you get to an answer. The interpretation students take is that that means that this must be a solution, namely that if x was equal to -1/2, that it would follow that x equals x plus 1. Students are interpreting, let me do this with better colors. Students are interpreting this as saying that, which it doesn't. And of course, as we've previously discussed, deductive reasoning goes one way. You've got to be careful about the direction of your interpretations. Okay, so with this nasty little problem in mind, notice legal algebra does not always give you solutions. So we have to go back up to this method that I think most students probably saw at some point in their mathematical developments. Note that we've done legal algebra, and if we do get down to an answer, how do we know that actually is a solution? Again, not immediately obvious. So there's a lot of questions that remain. So that's why I call this a bad method. This is a method that leaves you with arguably more questions than answers. So let's try to find a good method. What is a good means of solving systems of equations? We're going to have to do a perspective change. There's some points of view that we need to take, and some definitions that we need to make, some terminology, and it's going to take us a while to actually come up with this completely conclusive method, strategy for solving systems of equations, and we'll get to it, but there is a significant amount of building up. The first idea is to change our point of view. We are not looking at a bunch of equations. We are looking at a system. Think of it as a singular thing, a single system, as opposed to multiple equations. Of course, there are multiple equations that are inside of the system, but the point is we want to focus our attention on the system, not on individually the equations. Quick definition: if you have two systems, of course, you're going to be given one system, but if another system should be made by some method that we'll get to momentarily. We want to talk about what it means for those systems to be equivalent. This word is going to get used a lot, and we will, in this course, use the word equivalent in reference to systems if they have identical solution sets. That means that any solution to the first system must also be a solution to the second system, and any solution to the second system must also be a solution to the first system. So identical solution sets, not related, identical. Okay. All right, so it turns out that the next definition here, these things called elementary equation operations are going to play very importantly into our process for solving systems. I'm going to first tell you what these elementary equation operations are, and then subsequently I will tell you why we care about them and why they're interesting. Okay, so first, if you have a system, keep in mind that a system is made up of a bunch of equations. Right? We're thinking of the system, though, as a single thing. The first operation that we're going to talk about is interchanging two equations. So, for example, maybe the first and the third. Now, what happens if you take two equations and just switch their positions within the system? Well, come on, it's the same algebra. It's the exact same list of equations, at least in total, but the system is a little different. The equations have been reordered. Now, is that an important difference? It doesn't seem like it. It's going to turn out to have some relevance, and we'll get to that later. But this is our first example of what we call an elementary equation operation. Okay, next example. Adding a multiple of one equation to another equation. So I could take, for example, this equation here, and to that equation, I could add 4 times that equation. Add that into that second equation. So, okay, well that's another thing that you could do. This is another elementary equation operation. Okay, last of these 3 elementary equation operations. You can multiply one of the equations by a non-zero number. So I could take this third equation, for example, and I could multiply it through by 7. Now, it would again give me a different system. It's a little bit different anyway. Okay, now, why do we care about elementary equation operations? Importantly, now obviously these are all algebraically legal, right? If you take 2 equations, it is perfectly legal to add one to another, or to multiply by a scalar and then add to another, or rewrite them in different positions. I mean, this is all perfectly legal, but that's not the point. What makes these elementary equation operations special is that they are reversible. If you interchange 2 equations, you can interchange them back. If you add a multiple of one equation to another, you could then subtract that same multiple of that one equation to the other. Right? So anything that you do with an elementary equation operation, you can undo with legal algebra. Right? And then likewise, if you multiply an equation by critically a non-zero number, now it's got to be non-zero, that's an important little note, well, you can divide by that non-zero number, and that's why it's got to be non-zero. You're not allowed to divide by zeros. It's the fact that this is non-zero that makes this reversible. Okay. All right, so elementary equation operations are reversible is really the big point. And that leads us to this result. If you have a system, and if you apply elementary equation operations to get a new system, those systems are equivalent. Remember, equivalent means they have identical solution sets. So I want to show you why this is true. The idea is not such a big deal, really. Suppose I have a system, and suppose I apply elementary equation operations, and I'll color code this, I suppose. Elementary equation operations, perhaps several, right, to give us a new system. So this is our scenario. So we have these elementary equation operations that turn S1 into S2. Now, because these are reversible, that means that I can also turn these arrows around backwards. There would be a slightly different sequence of operations by which I could turn S2 into S1. All right, and now let's just think about the solutions. By the way, these are also elementary operations in red. So let's think about, for example, suppose we have some collection of solutions, x1, or well, let me write these down. A collection of numbers, I'm going to call them x1 through xn. Right? And suppose that these, well, I'll just do it like this. I'll say, suppose that those solve that equation, that system, excuse me, of equations. So when you choose these values of x, suppose it follows that that system of equations is satisfied. Well, following the arrows, the purple arrows that is, we see that that means that that same collection of numbers also satisfies that system of equations. Because the purple arrows are legal algebra, and that means that this being true forces that to be true. Okay, so we see that if you have a solution to S1, that must also be a solution to S2. That's because we've done legal algebra. Now, that's not sufficient to show equivalence, though. To show equivalence, we have to show that it also goes the other way. Suppose that I have a solution to S2. Does it necessarily follow that I also have a solution to S1? And remember, this has got to go both ways. We need for the solutions to S1 to be solutions to S2 and vice versa. So, well, critically, importantly, because these elementary row operations are not just legal, but also reversible, that means that I have legal algebra going that way. And that means that if I have a solution to S2, then it follows that those same numbers are solutions to S1. So this implies that. So it's critically because of the reversibility. It's because of that reversibility that I conclude the equivalence of these systems. Okay. All right, so this is our big picture strategy then for how we're going to make progress. It's not clear how we're going to solve the system exactly yet, but this is how we're going to make progress with solving a system. We're going to think of a system of equations as a single thing, as a system, and we're going to apply elementary equation operations to a system to turn it into another system. And because elementary equation operations are reversible, it will follow that they are equivalent as per the theorem that we just proved, as per this one. And therefore, the solutions that I find to the second system are the same as the solutions to the original system that I was interested in. So let's see an example of what this looks like in practice. So here is a system of equations. Now again, it's two equations. We're not thinking of that as two equations. We're thinking of this as a single thing. That is just a single system we're going to call S1. All right, now here I have done an elementary equation operation, and that elementary equation operation turns this system into that system. So now let's look at what this elementary equation operation was. The elementary equation operation was that I've replaced the second equation with itself plus this scalar minus 2 times the first equation. Right, so I've added a multiple of one equation to another equation, and that's what I put here. Right, so that equation had this elementary equation operation applied to it. Now, notice, of course, that turns a system into another system, other system, and so the first equation didn't change at all. Right? Go back to our list of elementary equation operations, and it is an elementary equation operation to do this, and only that. right? That's the only thing you do to the system. So that equation has to not change. All right. So we did an elementary equation operation, and that turned a system into another system. Okay, so did that help us? Well, it's hard to, not immediately clear. We still don't know the solutions. But notice it's a little simpler. And I was clever in my choice of operation to make something disappear. And we'll talk about the best strategies, etc., at a slightly later date. Okay, so here's another elementary equation operation. That turns this system into that system. Okay. And then another elementary equation operation that turns that one into that one. And at this point, actually, we see some really good news, and that is that I actually can, at a glance, tell you the complete set of solutions to that system. Because it's a really easy system, and I see x1 has to be 2 to solve that system. x2 has to be 1 to solve that system. Done, right? There's nothing else to know. I've not only found a solution, but I know that that's the only, any other solution other than 2, 1 would fail at least one of these equations, and therefore not satisfy the system. So, easy to see the exact complete set of solutions to that system. And because of equivalence, I can conclude that what I've found is also the exact set of solutions to that system. Okay. All right, a little bit of notation to refer to. You see here that I have circled numbers. That's just a notation I find convenient to refer to which equation in the previous system we're talking about. Critically, it's referring to an equation in the previous system. It is not referring to an equation in the original system, right? Only to the previous system. The point here is that we take a system, we turn it into another system, and then in order to make progress, we look only at that new system. And then that we turn into another system, like this. Okay. Importantly, look back and notice that these elementary equation operations doesn't say anything about, oh, take an equation from one system and combine it in some way with a different equation from a previous system. No. Nothing of the sort there is allowed, right? All elementary equation operations involve operations on equations within a single system. So there is no mix and match allowed. Okay. Another little notational observation that I'll make. I like to put the formula explaining where a given equation came from right next to the formula itself. The book has a different convention on this, and so just heads up for that. It's not really, I suppose, critically important, but I think mine is more natural. Okay. All right, so now one last little quick thing. We've got this process by which we can turn a system into another system, which in this case at least, and hopefully also in future cases, is easy to solve. Notice that I was careful to keep the x1s all in the same column. That's just being organized. And then the x2s are all in the same column. And then notice that the equal signs are all kind of vertically aligned as well. And then notice that the constants on the right-hand side all always on the same, in the same sort of column, if you will. Now, from an algebraic point of view, I suppose you don't have to do this, but it's convenient. It avoids confusion to do it this way. And if you just make a promise that you will always do it this way, then look at the handy little shorthand that you can use. Instead of writing a system of equations like that, you can say, well, look, this is always x1s. I mean, the x1 is implicit in that column, and that, as a aligned column as I'm drawing them. So why don't we just say, look, all I really need to keep track of then are these numbers. It's understood that this is the x1 column. So why do I need to write that down every time? Right? The only thing that ever changes when you do these elementary equation operations are these coefficients. So you just have to make a fixed choice, and you do have to fix it. You have to fix the order of the variables. You have to decide that that's going to be the x1 column, and that's going to be the x2 column, etc. And then this is going to be the constants column, and I'm always going to put the equal signs here. But once you've fixed those choices, you only have to write down that instead of that. Now, it's just going to save you a little bit of pencil lead or ink, time if you're writing on a tablet, but it is convenient. Now, it's going to turn out that there are much better reasons than convenience to make this shorthand. But at the moment, I'm just going to sell it as it's convenient. So this you might recognize as something called a matrix. Some of you have seen matrices before. There are a lot of things that you can do with matrices, and we will do a lot of things with matrices. But for the moment, it's a convenient shorthand for a system of equations. Okay. So a little bit of terminology. This is called the augmented matrix. It's the matrix that represents the entire system of equations. It's going to end up being convenient, though, to refer to the coefficient matrix. That's just this part of it. And the terminology is chosen because, of course, those are the numbers that are the coefficients of the variables. So, natural choice. This is called the vector of constants on the right-hand side of the equation. Okay. All right. So, last observation that I want to make about this shorthand is notice that once you've made this shorthand, what had been an equation within the system, its shorthand is as a row of the matrix. So, something to keep in mind as you go along, columns correspond to the various coefficients in the various equations of a given variable. So you might say columns correspond to variables, and rows correspond to equations. So if you are using this shorthand, and if you want to apply elementary equation operations, well, equations, being as they are just rows in the shorthand, elementary equation operations we can reinterpret as elementary row operations. And the whole point here is that rows are just equations in the shorthand. So, in fact, these are still elementary equation operations. This is just what they look like in the matrix shorthand. So, you'll recognize they're the exact same operations, interchanging two rows. Well, that's interchanging two equations. Adding a multiple of one row to another, well, that's adding a multiple of one equation to another, etc. Multiplying by a non-zero number, etc. Okay, so this is where elementary row operations come from. They're just shorthands for elementary equation operations.